So, after our discussion on human visual system, where we were trying to find out if some system approach is there in a biological visual system or visualization of an image in terms of collecting information by presenting it as image there. So, after that we could come to know that human visual system has few limitations and few things there which may be crucial for implementing a practical system which we like to devise. Finally, maybe for doing the image storage or further processing or transmission. So, towards that, after the human visual system, we have discussed little bit in terms of system approach. Let's move to the practical imaging system, which is a typical example I can give as digital camera there, which is nothing but a digital imaging system or purely an example of digital imaging system. So, in that system, if we need to use those approaches which are there in human visual system, which one human being perceive by taking the image from the scene, what are the components to be carefully incorporated in the system. So, those things should be intact in the digital system also, which we will be talking today. So, let us move towards this discussion where we may need to discuss at the very beginning about the sensors which will be sensing the practical happening or physical phenomena. So, image sensors are at the very beginning of this digital imaging system. After that, that imaging which is done maybe in various manner, out of which few will be discussed here, so that we get an impression on how imaging is done or image data acquisition is made in the digital camera. But I will like you to inform here, for the first 2 points, imaging sensors and various image acquisition system which I will be discussing here, up to this no such contribution of digital system will be there. Purely it will be in analog domain. But we are talking about a digital imaging system or digital system. So, to get into the digital part, we need to go for digital image acquisition separately as an elaborate discussion here, because our theme is for digital image processing, or in this lecture it is digital image acquisition. So, we will be devoting much more time on digital image acquisition after we take few examples on image acquisition in the second bullet what it is shown there. Now, after getting into digital image acquisition in that topic, you will see there are some limitations or there are some crucial points which we should not miss while going for digital imaging or making an analog image into digital form. For that, one theorem which is written down here, Shannon-Nyquist theorem, which is also to be discussed here, and we will see their effect also. And in between remaining things which will be discussed there, we will be taking example of those in terms of image. If we deviate from those, how the image gets corrupted. So, let us proceed in this direction. At the very beginning, about imaging sensors. While you are talking about sensor, in that case you are directly in touch of the physical happening or physical phenomena. Means practically in the physical domain, if something is happening there with which the digital system or a system will be interacting, that part is the sensor part. So, in that case automatically those physical energy is coming into picture. What is it? This is photon for the visual image. If I say the photon from the visual spectrum, or the spectrum we saw earlier, the wavelength from 400 to 700 nanometer. So, for those, if we consider in our human visual system, we have seen there two types of visions are there, photopic and scotopic, for which rod and cone cells are responsible, and in that scotopic vision is much more dominating because rod cells are larger in number. Now, in this third bullet, I have incorporated another point there. In terms of doing acquisition of color image, we need basically of three colors to handle there. One is red, green and blue, which is called RGB color component. But in that, one thing should be known here, that out of these three, green is much more dominating to our eyes. Or the same thing I will say in another language, our eyes are much more sensitive to the green lights than the remaining two. That is because if you see the practical one sensor here for color image sensing, you are seeing there with color it is represented, red, green and blue sensors are there. Sensors for red, green and blue color are kept there. One thing should carefully be noticed there, the density of green squares are more than the remaining two. This is the reason for which we will consider this density more compared to remaining two while designing a sensor for collecting the color image. Why it is? By looking again to the practical phenomena or human visual system where our eyes are much more sensitive to the green lights. There we need to give much more care to them. A layman can simply ask there, if our eyes are already sensitive to green, why should we take that much care? Because the information is automatically coming there. But I will say in another way, I am not going to distort anything whatever it is happening in the physical domain. I want to replicate the same thing or portray the same thing to the system. Now let them decide who is doing some perception or perceiving that one, which way they will be perceiving or what information they will be taking from that, it is up to them. So till we go to the processor, we don't have any chance in terms of practical system development. We should not go for that. On contrary, I will say we should take much more care on that color to which our eyes are sensitive more, because the error in that will be seen much more compared to the other two colors. And that is the only reason for which we need more density of greens than the red and blue. Fine. So if I take out individually there, now let's see what are those, which way I will able to make them do acquisition in my system. There are the practical sensors are kept in this fashion in an array, where alternate colors are kept there, and individually those are shown here, red, green and blue. If you see there, on top of every sensor individual part, there one small shade is there, that is actually a filter for all three. That means this sensor is devised in such a way that it will be passing only red light and remaining will be filtered out from it. So that sensor will be behaving as a red sensor. Similarly, for the others, green and blue, the sensor which we will be devising for a particular color, in that we will put the filter in such a way that remaining colors will be filtered out and only the desired color will be passed through. After I pass through the filter, remaining three parts, you are seeing the shades are of same color, or I will say those are of same material actually. They are responsible only for sensing the variation of the intensity of that particular color. Typical example how I will give, say red light is coming there, it has a particular wavelength which is different from the green, but say it is a sinusoidal wave with some amplitude there. Now if that amplitude is varying time to time or space to space, that variation will be sensed by the remaining part or the bottom part. Cannot I say that that variation can happen for green also or blue also? But since it has passed through different filters there, green filter will be passing in this green, the filter will be passing only the green light there, but the variations are corresponding to the green color. or the intensity variation due to green color. So if I get the signal from individual and see the variations and I mark them that this variation is for the red and this variation is for the green and this variation is for the blue, then my purpose is served. But I have to know that this variation is for which one. That my system knows and it has to know that. After that, they will be knowing that what color combination was there at particular time which was getting illuminated in the digital system what we are talking about there. Now in another time that can change. Again same set of colors will be coming there. Maybe light is same, but that is a band of frequencies there. So in that red and green and blue colors only will be collected there by this kind of arrangement. Remaining will not. From there only the actual image will be replicated. Fine. So this is the practical arrangement what we make. Let's go little bit inside of it, where this single one which at the top it is given there, that is again redrawn this part there without considering any color there. As if I am considering for a particular color, this signal is coming there as an energy which is given there, that is the energy which has come there. It may be red, may be green, may be blue. But it is about the sensor I am talking about, where the variation inside it I need to track, which is most important, or where the information is lying basically, and for which we are devising a system that repeatedly I am saying to collect the information in the physical happening. That may be red, may be green, may be blue. No need to confuse there. So I am generalizing that one with an energy. That energy is passed through a filter, respective filters, and then it has gone to the shaded, gray shaded part in which the signal, photonic energy or the light signal will be now changed to electrical signal. Typical example, photodiodes. If some light has come there and that has created a variation of intensity in it, the current through the diode, photodiode I am talking about, will be changing accordingly. That change is shown at the bottom there, voltage waveform output. Fine. Now, if you remember one circuitry there where one photodiode is used, you will be seeing there, you have to make the connection from the beginning. You have to make it biased there at the beginning, and then you will be keeping it open so that light comes on that and current through it changes, which was at a particular value when no illumination was there but some biasing was there. Now that biasing part is actually this power in which is said there. If further biasing you have much more, you need much more elaboration or realization on it, please think about one transistor. People say it is an active device. In which respect? Basically it can give you extra power. Where from it get? From the bias. What is that bias? Unless and until you bias the transistor, it is a dead element. You cannot consider it as an active one. It is simply a PNP or NPN junction semiconductor material kept there. After you bias it, it become active. Now you use it as an amplifier, so it will be active. This way. So biasing or external power in to the system is to be given there. So this power is like that. Just consider this way. So that your sensor is now active, so that it will be responding to you as per the light intensity varies on it. So after that, remaining things are housing only, which is kept on it, but we are now onwards will be interested about this signal which has come out from that sensor. If I ask you, is it a digital signal? Never. It is an analog signal, just like analog in the physical domain which was happening there. So analogous to the physical happening. Okay. So sensor output is analog signal. Now, if this way one sensor is there, now you want to make an array of that kind of sensors in a line that looks this way, where individual small blocks are that kind of small sensors. but they are kept on a straight path, so that that will behave like an array of sensors of that kind. Exactly same, just copy paste. Okay. Now I can make another arrangement which will be in a two-dimensional array, where individual elements are again same at like the top. It hardly matters to device. Exactly same thing, fundamental things are same. Only thing is that it is coming in another dimension, and here another dimension is added there. What is the advantage of doing this? We will see those after this. Let's see here in this example where few image acquisition systems through those sensors are discussed. Just like take the first single sensor for this diagram. Only one sensor is available to you. Using that, you want to do imaging. In that case, you need to have a drum first. On that, you will be keeping a photographic plate, and on which you will be tracing at each and every point at a particular time, where scanning for a particular area, you need an individual spot at particular instant, and then you will be scanning it in a particular row first, then you will be coming to another row, then on the other row. If I want to make it in mechanical way, which way should I do? Just like at the top, the sensor is given there, which is moving through this. That means one linear scanning can be, or linear scanning can be done. So for a particular position of the drum, one linear scanning is made. After it finishes that scan, then you rotate the drum. You need to know at what angle you will be rotating the drum. That means there is a difference between, or distance between two rows. After you rotate it, again you will be doing the same job from scanning from left to right. Again come to the next angle, again scan it. So this way if you do the two-dimensional image, what you see, that can be done acquisition by using a single sensor. But the same job can be done in one go. If I make the arrangement such that it is in a linear array, the number of sensors are kept, and then the same array is just moved from top to bottom, the way it is done in the linear strip. So much more comfortable, but much more cost you have to pay. More sensors are required there. Okay. Would not it be better if I would get in a one click the full scene? Here also I need a scan from top to bottom or left to right, but one scan. Compared to the single one, it is better. But if I want in a one go, just like click and receive. So I may devise one system where in an array, in a matrix form, the individual sensors will be kept as we are seeing there. So total two-dimensional thing is now directly going to trace the image to all the spatial positions which are there illuminated. So that way the arrangement will vary for different systems there, which can be implemented by using the same sensor with the same fundamental idea what we have discussed just 1 minute back. Okay. Now let's come to this discussion where we may like to consider 3D object to image. As we were discussing at the very beginning, the 3D objects are also imaged there. So in place of 2D, if you are talking about third dimension, so you need to take care of the third dimension also. But as I said you, we see the 2D only, and remaining third dimension we process by our mind that something is there might be. How? Basically our eyes also do that way. We see the 2D, but since some shade is coming behind some places, so we are thinking that maybe something is there behind. That's why I am not able to see the back, but still I guess that this way the back has come by seeing the curvature of it. but that is our processor which make us available to see. Okay, take the same idea for device in the system. In this, what we will do, we will take the image of a particular cross section at a time, and then we will process them or reconstruct them in such a way that third dimension also come into picture. Okay. So, the typical example is given here in terms of X-ray scanning for 3D object, where this is the object which is to be scanned and which is to be passed through this circular shape at keeping it at the axis of it, means passing through the center of it. Now, for a particular instant when it is kept there, in this the X-ray source will be kept there which has an angle towards the center, because the curvature is same. So, signals which are transmitted from this particular finite area but focused to the center only. So, all will be concentrated to the center. In between they will be facing the other places of this region, but they are passing through that. Now, if this X-ray is passed through, that means nothing is there in between to object it. But if it is not allowed to pass through, that means in the other side, if I put one X-ray sensitive material there, that will not able to sense anything there, even though the sensor is kept there, that nothing is sensed, but remaining part for which no object was there, things are sensed at a particular go, I am saying. Now, we will rotate it. If we rotate this, the same thing will happen for each and individual point. So, if one strip of sensors which we have discussed just now, that I keep in this, and one sensor, one X-ray source is kept here which is moving. So, one scan of this means one 2D is scanned there. After one scan is complete, I will move it once. So, next cross section, as if like individual cross sections I am chopping. So, this way 3D will be imaged, but think about the signals which were collected by the sensors which were kept as strips there. Think about an individual sensor which was collecting those signals there for one scan, then movement in the third dimension, another scan this way. Those are all there as a signal in your memory, but they are not in the proper form like which you want to see in this form. That will not give you directly the 3D notion. You have to now track them at what condition, where was the source, where was the sensor, and where the signal is there and what is its amplitude if the rotation of this source is made from 0 to 360 degree. Now, for that, what was the third dimension's coordinate? Everything should be in my memory, so that I can recollect them and I can put them together to reconstruct by this another device which is called image reconstructor, so that I get the actual image by putting individual cross sections one after another and present the third image. But so many complexities may come there. Fundamental thing what we need to know here, if a sensor is doing some acquisition there, what is it basically? This is a simply intensity value or some amplitude value of voltage variation. That we need to consider more here. Why? Because the course is on image processing. If you want to do processing, those processings are basically on that level. That is the fundamental point, and remaining things are additional things for processing there. They are very limited actually. That depends on the mechanical system. If the mechanical system is made much more sophisticated, those processing will be going down, but scope is there. That I would like to highlight here. That scope is there in that level also, so that my electronic system gets less burdened due to my evolved mechanical system given to that particular arrangement. But for electronic processing, we have another thing where the electronic or electrical voltages are to be considered, where we will be focusing about the variation of sensor output voltages. Please try to stick to those points. Let's take the typical example of a digital camera, what we used to see working in front of us and giving the image before clicking, after clicking also. Views are there which is passing through your lens, and then it is coming to your screen, and then you are deciding whether it is to be taken or not, you are clicking. So, this kind of one digital camera is given here, where basic components are only given here. So, if you come from the front in the problem domain, what we said means this is to be imaged. Now, that should pass through one lens, just like our human visual system, it was there. That is passing through a lens. Because of that optical geometry, it will be inverted. So, that inverted image, it has come there. It hardly matters to you make it another inversion so that you get the actual way. That does not matter actually. After you get this one, which is maybe through the sensors you have collected in your digital camera now. Unlike your human visual system, now you are coming to the digital camera there. So, those sensors which we have discussed now, those are kept in between, which has imaged the A in this form. Still it is analog. Okay? Now, if it is analog, I need to take care of it so that I handle this in terms of digital form or by my digital processors. So, first step come that analog signal which has come after the sensor to be digitized. So, for that we need one device like analog to digital converter, or simply we will say ADC. So, this is that ADC we are talking about. After you get ADC, now your LED screen or LCD screens which are there to see the scene, that can be projected in this form or manipulated in that form and present to your eyes that yes, this is the scene, you are ready to take its photograph permanently. But before you take, things are done. Okay? Now, that one you can like to, after you digitize it, memories are there available to you to keep them stored, as we were discussing earlier also. And after that, if you want to process them, processors are there inside the camera itself. And digital outputs are also available to you at the camera. So, basically, we are discussing about this part and this part now. And slowly, we are trying to move towards this. What is the function of this processor? And remaining things are just ancillary things. Okay. So, we are moving towards this. So, today we will be discussing up to this part. Analog to digital conversion of image. Let us move further. Any doubt? Let us move to this scenario where, say, one object scene is here which is illuminated by one light source there and which is reflecting its energy through this, and that has passed through sensors. Since we had talked about the sensors, now I am doing some incremental discussion on it, like I am saying internal image plane there. It is not the sensor. Sensor has already sensed and finally it has imaged the object there in this form in a particular plane of with finite area. Okay? Now, in between this arrangement, if you see there, that is basically to make the total scene available in a smaller area where the bigger scene will be imaged. Just like the object size and the image size, or the object height or the image height. Depending on the image height, how much image height you want, that will be decided by this mechanical arrangement, or the lens basically and its open space there. So, why do I need to care that much on that part? Because the lens, the sensors which we will be using, the area of the sensors on which that light will be falling to sense its variation, I think that is much less than your size of the digital camera. Is not it? Whatever may be the size of the sensor, means all sensors what are kept there, the size of the sensor cannot be at least more than your camera size, and which is becoming day by day more smaller and smaller. So with that small space, sensors are there in a further smaller spatial dimension, with some spatial dimension. In that you want to put that bigger scene there, for that this small arrangement is made there. But after it has come to the sensors and after it has passed through the sensors, after sensing its physical phenomena, physical variations there, those variations we have put in an image which you can consider as an image which is an analog only. So in that the object which was there, exactly same thing is replicated. Means sensor output is just projected somewhere. This is the internal image plane, but our digital computers don't handle those. They need only digital form. So I need to digitize this part in this form, where I will not say this is the digital image basically. This is basically a discretized image. It is just discretized the space and also the amplitude value. Which way we will discuss. So this way things are different from analog to our digital domain, where in between this discretization is coming into picture. But before knowing about discretization and digital image there, we need to consider these two first, sampling and quantization. I will again ask you to recollect our ideas on sampling and quantization of a single dimension analog signals, what we have seen in our earlier courses. Please come to this with reference to the same object which we have considered. This is a two-dimensional object which I need to consider for quantization, before that sampling of it, and then we will move for digitization at the end. So let us start from beginning. So this is the two-dimensional plane. We would like to use the same thing like for analog single dimension we were doing. So I will scan a single line. Be careful here. Most of the people will be confusing in this part, where I am doing a transition from input to from one dimension to two dimension. That hardly matters, but the variation of the signal, which way it happens, that is to be understood here carefully. It is here. If I am scanning from A to B, what do I scanning here? What do I need to scan here? Basically the intensity values or the black and white spots which are there, those are I am scanning. So I am scanning throughout from A to B, and at the beginning I am saying it is white, means full light. So the amplitude, the sensors which have given me the light, given me the electrical signal with some voltage level, those are very high because full light is there. Intensity of light is very high there. So those are presented here. After scanning, the electrical voltage what the sensors have given for that particular row is given here from A to B. This is a single row, no two dimension. It is a single row and its voltage variation according to the variation here after this till this one. Intensity has gone down, towards dark is going, so voltage level has gone down there. But in between if you see here some whitish part has come, so it tried to go little up. I think it is not that white like the outside one, just like this, it is not that white, so it could not reach up to that point. So I think you are able to realize it that yes, the intensity variations which were happening there, my sensors have sensed those in a particular row and that is projected here. Now after I get it, Now I leave my physical domain. I will be fully on the electrical domain, where the variation or the scene which is to be understood for this particular row as this. I could easily choose this AB in the other place or in the other row. I would get another variation of intensities there, but the signal would be this electrical analog signal. Fine. Now, this is the analog signal, like the analog signal, analog to digital conversion you have made for a single dimension. This is the place where I am putting your known ideas and using them to go to the second one. So, if I make the difference between those two, earlier we used to consider the single one, now it is two. How does it matter if I talk about not a single line but a multiple depending on different rows? Individually the rows I will be considering, and those are single dimension. Only thing is that I have to make my system little bit more burden, or it should be tracking the another dimension through which I have to scan further. First left to right single dimension, then another row left to right. So individual if I will be processing, things are done. Basically we do that way. For information, our eyes also do that way only. That's why the local brightness, what I was talking about, local brightness adaptation, it was because of that. Because effect of one local position was coming to the other. So when we are devising something, we are not deviating from the actual happening. Otherwise, so many changes will come into the picture. Okay? So fundamental things are exactly same. So let's take this one single row there of that complete image, which can be easily extended to the other row as I said there. Now I will be concentrating on this part. If you see there, in horizontal axis, how many individual points are there? Infinite number of. That depends on how you have scanned from left to right at what gap. But if you see by your eyes or an analog system which has scanned the physical happening, I consider ideally it is infinite. But our digital computers cannot take the infinite number. These are fundamental things for digital signal processing I am talking about, where we go for analog to digital conversion, which is a common course as a basic electronics. Okay? Nothing other than that. So if it is infinite number, we need to make it finite. How could we do? I can take few samples of it so that it represents everything. So let's few samples from it. So here let me take these samples, not the all in the horizontal axis. This is called sampling. If I am saying it is a two-dimensional plane, in that I want to scan through a row, in that I had to scan each and every point which were number of infinite. Now I will say that no, I will not go that way. I will take 1 centimeter gap in between. That means in between 1 centimeter is lost. Let it be lost. That is the loss in the digital system. Okay? That we will like to make as less as possible. But we have a limitation that we have to make that sampling, because we will be taking the sample at that position. Means what? Sample of information. Where is the information? Information is in the vertical axis. In other axis, horizontal axis, no information is there. There is the independent variable you are defining. I am starting from that point, then I am coming here, here and here. That means the two-dimensional plane which is there of some dimension there with one origin there. You are increasing x value, you are increasing y value, and you are visiting each and every point, and you are collecting sample from those places. Okay? Just like if I want to get the sample of the students here, I will be taking here and here. For that I need to move to that particular place. So the spatial coordinate I know, but now at what spatial coordinate I will be moving, that I am deciding by sampling that where I will be getting the sample of the information. Fine. So basically to collect the information we are sampling at this instant so that I get this sample. where the information is lying in the variation of electrical voltage. Fine. Now, while collecting these samples from here, now tell me, if I consider the signals in general, maybe the x-axis or the horizontal axis is discretized, but what is the value in the y-axis you may get for different signals? For this particular scan, you are seeing that for this sampling you are getting here, then here. But if you would scan another place, like say here, this signal would be different. In that case, there may happen that one signal is coming here in between. Be careful. This is a single sample in the other axis I have taken. In that, if I go for a variation where the voltage level can vary from lowest to highest point, what is the chance? Chance is that depending on the image, the variation of the voltage can be anywhere in between. Because your range of presentation or consideration is from this lowest value to the highest value. Now, the signals can take any value in between, which is again an infinite number. Okay? So, that infinite number again I need to tackle. That also is not possible. So, for that we will be quantizing the levels, that we will be not consider the continuous one, but few levels will be considered which are quantized in a particular number, like say 100, 200, 300, 400, this way. So, that way these levels are also quantized or discretized. So, this is called quantization, but not this. This is sampling and this other side is the quantization, basically quantization of the voltage level or in the platform where the information is actually kept, and sampling is the sample where you will be collecting the information of it. Okay? So, these are two important things while you are moving from analog domain to digital domain. Now, a simple question can come there. How to decide this quantization level or this discretized level in the spatial domain, where this horizontal axis is nothing but a spatial variation. If I say this is y and this is x, this x y dimension of a two-dimensional plane. Okay. So, that I have discretized in a particular fashion, and this amplitude level also I have discretized. Simple example I will give you. The sampling of the thing is not it like the matrix what you have represented there, the inter-element spacing. If a LED screen is there, if one LED screen is there, what is the spatial resolution of it? Interpixel distance? Is not it? That interpixel distance if you are talking about, that means I will ask you, what is about the information or the signal variation or the intensity variation in between two pixels? You will be silent because you do not know, because you have missed them, because you want to present the image with those samples. So, those are the samples. Now, in the intensity variation if you talk about, that also has limitation, that how many intensity levels are there which you can represent. Those are in other way. Now, the spatial coordinates which you are considering as your location of the LEDs, that is depending on how many LEDs or how many number of pixels you will be putting to your screen, or can I say this way, that how many sensors I will be keeping in a particular area. Presentation is on the screen, other side is the sensor. So, in the sensor also I have a limitation that at what location I will be putting the sensor there, and its center is somewhere. Now, it has a physical dimension of area. Now, it cannot be more than that. Is not it like in this other image, if I consider each and individual squares as sensors, I consider individual squares are individual sensors, center of it is the reference of that one. Those will be collected by the sensor of this size. So, sensor also will have some physical dimension. So, depending on this, from here to here, this will be called the resolution or the sampling which is made in this. Okay. Now, in other side, if you see here, continuously from dark to white it is going. Is it really continuous? It may not be, because in between some levels are missed. Now, more the number of levels you put there, more the number of digital bits you need to represent them. If 2 levels are there, only 0 and 1 is sufficient. If 4 levels are there, 2 bits are required there, 0 0, 0 1, 1 0, 1 1. So, that way the number of levels you increase, number of bits are required more, or bit depth increases. I think you remember the term bit depth which we have already discussed. So, the quantization levels are related to the bit depth, and this sampling of it or samples from where it will be taken there, that depends on at what gap you will able to take the samples there. That has a limit, and that has so many crucial points there to discuss. If I say the sampling or the samples from where I have to take, that means per centimeter how many pixels are there. That is the frequency I am defining. Come to the known knowledge of yours. If I say one signal is of 50 hertz, what do you mean? Means a sinusoidal wave, say, of 50 hertz will be having its complete cycle 50 times per second. I will not say second, I will say per unit time. The number of times it will be repeating in a unit time, that is frequency with unit hertz, means second inverse. But here the frequency we are talking about, that is not have unit of hertz or unit of second inverse. I will say it is length inverse, meter inverse, centimeter inverse, or millimeter inverse. Okay. Now, before I go for this Shannon-Nyquist theorem, first let me talk about this F max. F max means the maximum frequency at which the intensity values varies in your image. Maximum frequency of variation of intensity in your image which is presented to you. What does it mean? Please see here. If you see here in a particular unit which way the up and down is happening, and if some repetition is there in it, at what rate it is happening, means how faster, crudely speaking, how faster the intensity values are varying. If it is more speedy, that means the rate will be more, then frequency will be more there. So, first you need to track that, or you need to know that what is the maximum limit. Okay. Now, if you want to get the sample of those, you need to get the sample of it twice of that one. That means one chopper will be there which should run 2 times of the F max. If that goes for 10 variation per second, here you will be saying 20 variations per second with which you will be chopping. So, at least 2 per complete cycle. At least 2 per complete cycle. That this Shannon says that if you take that way, then your reconstruction of the digital signal, digital waveform into analog form will be fine. Otherwise, it will be corrupted by the error. This theorem is well proved and well accepted and well working. He says that f sampling frequency should be greater than equals to f max, 2 f max. Now, here I am putting this d in it. D is of length, d is of unit of length, means it is a interspatial distance between two samples, or crudely if you say between two pixels also sometime. Okay. So, if I say two pixels have a particular distance, in that you have a signal which has a variation of f max. If f max is so high that d is not kept with this consideration, then your image is not properly stored somewhere, or you will not be restored the image in the proper form. So, you have to always maintain this d distance with this relation, where beforehand you have to know what is the maximum frequency you will be handling there, or what is the maximum variation of the intensity values you will be handling there in your system. It is not in the system specification. Okay. So, which way you will be deciding your interspatial distances, that is decided by this. If you deviate from it, see there, if you deviate from it externally, whatever may be your scene, this external shade of this kind you will find there. If your Fs means sampling by which you are going there, that is going less than 2 f max, those errors are called aliasing error, which is a foreign thing will be coming to your image and it will be disturbed. So, you will be liking to always make Fs much higher than 2 f max, so that you guarantee the proper reconstruction or proper handling of the image. So, Shannon theorem, as per Shannon theorem, we should consider this sampling frequency Fs, which is having unit of length inverse in this form. I have talked about sampling, but what is about this number of pixels if it is changed? You may say that I had to have the sampling frequency this much, for that I need to have the arrangement of sensors to keep closer, but I could not make it. So, it will be deviating. So, in that case, if I increase the distance or decrease the number of pixels in a particular area, in that case your image is again distorted. Even though you are maintaining that Fs greater than equals to 2 f max, still your image is deformed, because you did not take the number of pixels in a particular area of higher value. Just like this is the image of higher dimension, it is kept there, but here, see here, number of pixels if it is reduced there, things are gone there. Simple philosophy. Why? Because you do not have scope to present those in between values. So, you are extrapolating them by the same value which is at the center there. So, size of the area of the square unit what we have seen there, that has got increased there. So, this is that effect. One term I have mentioned here, keeping the quantization level same. What does it mean? It means the number of levels what you have assigned for considering the complete range of variation of the electrical voltage there, what I said, which is basically the image intensity variation. If it is of higher number of levels given there, that means quantization level is more. If it is less, in that case you have to pay somewhere. But in this particular images what you are seeing here, those quantization levels are same for all, that is not disturbed. Only the number of pixels are changed from there to here, it is decreased. But what happens if we keep the number of pixels same, but decrease the quantization levels, number of quantization levels, or decrease the bit depth? That means number of bits will be required less if you decrease the number of quantized levels there. That way, if you see the action there, you see from beginning to end, where only two levels are used, 0 and 1 means black and complete white to represent the same image. That doesn't give that much extraordinary thing, but if you see this image and this image or in between these images, particularly see this image in this. Compare it from the first one. In that you are seeing a continuous variation of the quantization of the gray values there, but here one extra contouring is happening in between, just like one shade of color is here, here and here. This way it has come. This is because of reduction of the quantization values. Why it is? Because when you have reduced the quantization levels, that means earlier which was in a different level close to one another, I am saying. Earlier which was say of 2 quantization level, which you have made 1 now to reduce the quantization number of quantization levels. So nearby 2 gray values have now become same. Earlier it was 2, now it is single. So you don't have any chance to represent those individual values. So for that you have to put the same value. Another point, if one image is given like that, which is a continuous shade of one gray values there, chance is there that nearby values will be almost similar to that. But you don't have any scope to represent those individual quantization levels. In place of that, you are putting the same value. So obviously, as if like in the same region, in a particular strip, they are having the same value, but actually it is not, which could be found if we would make the individual quantization levels there. That means there basically were many gray values there, but those my limitation is that I could not allocate those. I have allocated limited number. So they are giving a contour of this kind. These are called false contouring, which comes because of this reduction of quantization level, even though you keep the number of pixels same. Okay? So these are the few points which are crucial in digital images when you go for making analog image into digital form and take in your digital system for further processing, maybe in your other imaging systems other than digital camera. Okay? Thank you for today.